All right, what is up, guys? Hoping you're having a good weekend. Just gonna finish some of these notes that we didn't get to. I want to finish some of the notes that I think you could probably do a pretty decent job of understanding on your own, just so we can catch up with the other pre-cal classes and get back on our way, okay? All right, so first thing we want to do is we want to finish filling out our BFF, our basic family of functions here, okay? So this first function we're going to fill out is the absolute value function, y equals the absolute value of x. Okay, we've seen this a lot already, okay? We put our vertex, here's what this looks like. We put our vertex here at the origin, 0, 0. We draw a line here with a positive slope of 1. All right, and then a line here with a negative slope of 1, negative 1, sorry. Slope of negative 1, okay? Looks like that, just like a V, okay? So the domain of this function just keeps going on, right? Just keeps going to the right forever, keeps going to the left forever, these arrows here. So, and again, you can see that there's nothing we can't plug in for x, so the domain is all reals. So negative infinity, positive infinity with parentheses. The range here, okay? So that's all the set of possible y values, okay? Notice I have nothing below the x-axis here. There's nothing below that, so my function's never negative, but it can equal 0. It equals 0. My y value is 0 here at the origin, and then to the left and right here, I just go up to positive infinity forever. So my range is 0 to positive infinity, and then that 0 gets a bracket because 0 is included as one of my y values, okay? Continuity, right? There's no discontinuities. There are no holes, asymptotes, or jumps. So we say it's continuous on negative infinity to positive infinity, okay? Increasing and decreasing, Okay, notice to the left here as my x increases, as I go to the right, my y goes down. Okay? So I'm decreasing on negative infinity to 0. That 0 gets a parenthesis, okay? The 0 gets a parenthesis, okay? And I'm increasing, okay, so let's look to the right of 0. As x goes to the right, look at my function, it's going up. My y goes up, okay? So increasing on 0 to positive infinity. Okay? Symmetry. Look, what do we got here? So this graph is a mirror image. It's a mirror image across the y-axis, okay? Another thing we note is that the absolute value of x equals the absolute value of negative x. So our symmetry here is even. Our boundedness, right? So for boundedness above, my function is not bounded above. Why? Again, my y just keeps going on to infinity. We can look at the range here, actually, right? It's positive infinity, but I am bounded below because my y value never goes below 0. There's nothing down here, okay? So boundedness is bounded below. Local and absolute extrema. All right, here. Where is there a minimum y value somewhere? Yes, there is, right here. Right, my y does not go below 0, so it's a minimum, right? Bottoms out at y equals 0, and then it goes back up again, okay? So my local extrema is 0, 0, and that's also my absolute minimum, okay? Horizontal asymptote, there's no discontinuities, so there can't be any vertical asymptotes, so no vertical asymptotes. No vertical asymptotes, and then there's no horizontal asymptotes either. Okay, there's no horizontal asymptotes, okay. I just keep going up forever in both directions, so there's no horizontal asymptotes. End behavior, right? So as my function goes to negative infinity, right? Look what happens. My y just keeps going on up and up and up to positive infinity. All right. Then since my function is even, and you can see this on the graph, as x goes to positive infinity, my function goes to positive infinity, okay? So that's what we see on my graph there, all right? All right, so pause, rewind if you need to. Okay, hopefully that makes sense. Greatest integer function. This is one we saw in class today. I'm filming this on Friday, the day we took the quiz. So the greatest integer function, we write y equals int x, but that probably doesn't mean anything to you. Hopefully it will in a minute. Okay, int x, okay? So what does this mean? What does this mean? Okay. All right. Say I have a random number. Let's say you guys gave me 7 halves today. 7 halves, okay? Let's say x equals 7 halves, okay? If we plug in x equals 7 halves, what does my y equal? What does my y equal? Here's how this works, okay? So int 7 halves. What this function does, what the int function does, let's draw a number line. All right? We've got 7 halves here. That's equal to 3.5. Okay? So then let's plot some of these integers to the left. -3, -2. Wait, not -3. Sorry, what am I thinking? 3, +3, +2, +1, ... Okay? What this does is what this function outputs is it takes the first integer to the left of 7 halves. I plug 7 halves in here. It takes the first integer to the left of 7 halves, right? That's 3. That's 3, right? We got 3 right here, and it outputs that number, right? So the int function outputs the greatest integer, which is less than x. All right, so if I plugged in an x of 7 halves, my greatest integer, there's a bunch of integers that are less than 7 halves, right? All the negative numbers, 0, 1, 2, 3. Okay, the greatest integer that's less than 7 halves is 3. So it outputs +3. Okay, another example would be, let's say, int of 5/3. Right? That's the same thing as int of, what is 5/3 as a decimal? Is that 1.6 repeating? So it's about 1.6 repeating. Okay. Yeah, that's 1.6 repeating. What it's going to do, it's going to output the greatest integer, which is less than 1.6. That's 1. So the next integer down. The next integer down. Okay. That's how that works. Okay. So what does this graph look like? Okay. So let's start at 0. Okay, we put a vertex there, a point there. I'm going to do this in pink, actually. 0. What the heck? Where'd it go? Oh, there we go. All right. So if I plug in a number between 0 and 1, so any number in this interval here, if I plug in a number in from 0 or 1, right? For all the numbers 0, 0, and then right before 1, so any decimal between 0 and 1, the int function is going to output 0. It's going to give me a y value of 0. Okay? Right? If we put int 1/2, right, the next integer below 1/2 is 0. Int like 0.6, same thing. The next integer below 0.6 is 0, and so on, okay? I made that on the wrong side of my axes, didn't I? Sorry. All right, but int 1, if I plug in x equals 1 here, that's actually going to map to 1. So the way I do this is I draw a circle right here to say that this says that the circle, the hollow circle says that int of 1 is not equal to 0. And then the solid dot here indicates that int 1 equals 1. Okay? So this, I'm going to keep drawing steps. This keeps repeating, right? Okay. So if I plug in a number between 1 and 2, a decimal between 1 and 2, that's going to go to 1. So that's all at y equal 1. If I plug in a number between 2 and 3, it's going to go to 2. If I plug in a number between 3 or 4, that's going to output 4. Okay, so just all these steps right here. All right, and so on. Similarly, same thing for the negative numbers. So if I input a number between -1 and 0, right, the next smallest integer, so like -0.5, that would go to -1, because that's the greatest integer, which is smaller. It's the first integer to the left of -7.5. The greatest integer, which is less than -0.5, okay? Right, and so on and so forth, okay? So let's erase this so we don't confuse anyone. All right, so the domain on my graph, right? I can plug in any number I want. All right, I can plug any number I want into here, okay? Let's highlight this. Plug any number I want into it, -infinity to +infinity. The range, right? I can get any integer out, right? I can get out like -3, or even a smaller integer, -2, -1, 0, 1, 2, 3, 4, ... All right. So all the integers. This set is denoted with this fancy Z right here with a bar in the middle. The range is the set of all integers, right? I can't get a fraction or a decimal out of this, but I can get an integer out. -1, -2. -3, 0, 1, 2, 3, okay? All right, continuity. Right, it's not continuous, right? It has what's called a jump discontinuity at every integer. It has a jump discontinuity at if x equals an integer, so jump discontinuity at every integer. So what that means is, all right, here's our x-axis. As we're going along our x-axis, right, I'm going along in my graph. When I hit 1, it jumps up. There's a little gap right here. That's a discontinuity, okay? Boom, jump up. Boom, I jump up. Okay, so there's a little gap here between my y values. So that's called a jump discontinuity, and that happens at all my integer values of x. Okay, so jump discontinuity at every integer. Increasing, decreasing. All right, so the notes key says that it's increasing on -infinity to infinity, +infinity. Okay. Symmetry. Do we have any symmetry here? There's no even symmetry, right? I'm not reflected across the y-axis. All right. Let's think about this. I don't think there's odd symmetry. Let's think about this, right? Recall that if a function has odd symmetry, then that implies that f of -x equals -f of x. Okay, so let's think about this. Int of -1, that would be equal to -1, right? Okay, int of +1 is 1, right? Okay, so it holds, right, which is equal to negative int -1, right? So that net 1 is equal to negative 1. That's equal to negative 1, which equals negative int of negative 1, right? So int of 1 equals negative int of negative 1. So it works for x equals 1, so we're thinking, okay, maybe it does have odd symmetry, right? This condition does hold for x equals negative 1. Let's think of like x equals 0.5. So like int of negative 0.5 equals, that's going to be what? Negative 1? Negative 1. Yep. Int of positive 0.5 is going to be 0. Uh-oh. So here we have that, so negative, so int of 0.5 equals 0. Right, if this were odd, then we'd have to have int of negative 0.5. We'd have to have that be negative 0, because then it'd be negative int of 0.5. That's not the case here, right? Int of negative 0.5 is negative 1. So this is not true. We've broken my odd symmetry rule. So this has no odd symmetry, none. Boundedness, no, none. It's not bounded. Right? Just keeps going up and up and up and up and down and down and down and down. Okay? Local extrema, none. Absolute extrema is none. Horizontal asymptotes is none. No vertical asymptotes. Okay. End behavior. Let's talk about the end behavior of this graph. Okay, let me erase all this. Okay. Okay, let's look at this. So the limit of f of x as x goes to negative infinity, right? As it goes to negative infinity, right? As my x goes to the left, I just keep going down and down and down forever. Okay, I'll draw like little ellipses here to say that I keep drawing an infinite number of steps. So it's negative infinity. My limit of f of x as x goes to positive infinity, right? As my x goes to the right, my y should keep going up and up and up and up and up. So that equals positive infinity, okay? Greatest integer function. Rewind, watch, slow down, whatever you need to do, okay? Next function is the logistic function, okay? Excuse me. This is y equals 1 over, it's going to be 1 minus e to the negative x, I believe. Let me double check that. Yes, it is. Sweet. 1 all over 1, it's a minus, right? Let me triple check. Oh, yeah. Oh, it's a plus. Sweet. It's 1 all over 1 plus e to the negative x. E to the negative x, okay? The domain for this one, so here's what this function looks like, okay? So here's my x-axis. Here's my y-axis, okay? I'm going to draw a little dash through here. All right, so this is y equals 0. And then I'm going to draw a dash through here, and I'm going to explicitly label this dash line y equals 1. So here's what this function looks like, okay? So at y, the point 0, at x equals 0, my y equals 1/2, so let's plot that point. That's where I cross the y-axis, okay? What happens is this. Okay, so it's kind of a little sideways S there. All right, so I start here and then I go up to this horizontal asymptote at y equals positive 1. I go down to this, as I go to the left, I go down to this horizontal asymptote at y equals 0, okay? The domain here, notice there's nothing I can't plug in for x, so the domain is all reals. The range, all right? Notice how I'm bounded below and above. My graph never dips below y equals 0. It never dips above y equals 1. And actually, it never touches y equals 0, y equals 1 either, right? So my range is 0 to 1 with parentheses. Continuity is continuous everywhere. There's no asymptotes or holes or jumps. Okay. Increasing and decreasing. Okay, so for this one, I'm increasing everywhere. I'm increasing everywhere. Okay, symmetry. So there's no even symmetry, right? Because it's not a reflection across the y-axis. Odd symmetry, there actually isn't any odd symmetry either. Because recall, okay, keep in mind, guys, my origin is down here. Okay, so if I rotate this graph around, actually I think I can do that. If I rotate this graph around, all right, that's trippy. That's very trippy. If I rotate my graph around, I actually don't get the same thing I started with. I get a little translation down. Okay, so no odd symmetry. There's no odd symmetry. Boundedness, right? It's bounded. It's bounded, right? That means both. It's bounded above and below, right? Never goes above y equals 1. Never goes below y equals 0. Local extrema, none. No peaks, so there's no peaks or troughs, right? And then absolute extrema, none. Horizontal asymptotes, right? You can see those right here. Y equals 1 and y equals 0. And then no vertical asymptotes, right? I can never have 0 in this denominator, so no vertical asymptotes, but we can see on the graph, right? As I go to infinity, I get closer and closer to 1. As I go to negative infinity, I get closer and closer to 0. So that leads into our end behavior. Limit of f of x as x goes to positive infinity equals 1, right? As my x goes to the right forever. This curve up here, the graph up here gets closer and closer and closer to 1, okay? And same for as we go to the left, we get closer and closer to 0. So the limit of f of x as x goes to negative infinity equals 0. Okay? So that's logistic functions. So we're done with our basic family of functions. So now we can go down and do these textbook problems. Okay, so we have 19, 20, 21, 22, 23, 24, and 25, 26, 27, 28. So let's go over here to our book problems. Okay, I've highlighted them. We need to do 26, 27, and 28 as well. So let me highlight those. So these are the problems we're going to do. Okay, so 19 asks for the 4. So here's the directions. Identify which of the 12 basic functions. That's my basic family of functions. Fit the description given. So let's look at the 4 basic functions that are odd over here. 4 basic functions that are odd. Okay, looks like we've got sine. Sine's got that odd symmetry. Sine's got that odd symmetry. Okay, we're looking for stuff that can be rotated. Odd symmetry, reciprocal function. Cubing function, symmetry is odd. Squaring function has even symmetry. Identity function has odd symmetry. Okay, good. So we've got, so there's 4 of them here. We've got 1 over x, x cubed, x, and sine of x have odd symmetry. And again, that means we can flip the graph upside down and we have the same function. So let me do that for, I guess this one I can do it for. The reciprocal function, right? This is odd symmetry. That means, let's copy that, paste. Right, if I overlay this, oh man, I gotta precise. Right, if I rotate it 180 degrees, I get the same function. Well, about the same function. If my art skills were better. All right, let's go back to the book problems. Okay, so that's number 20. 6 functions that are increasing on their entire domains. Okay. X cubed. X, that's always increasing. This is always increasing. The square root function is always increasing. Exponential function is always increasing. Natural logarithm is always increasing. All right. And greatest integer function and logistic function are always increasing, okay? Let's go back and fill that in. Okay. So we have x, int x, e to the x, square root of x, logistic, and ln of x, natural log of x, okay? They want the 3 functions that are decreasing on the interval negative infinity to 0. So let's go and do that. Whoops. So decreasing negative infinity to 0. Here's one. It's decreasing negative infinity to 0, so absolute value. Here's another one, negative infinity to 0. We're decreasing. We're actually always decreasing for this one. And for x squared, we're decreasing from negative infinity to 0, okay? So this one's going to be x squared, absolute value of x, and what was the other one? The reciprocal function, 1 over x, okay? The 3 functions with infinitely many local extrema. Okay. Let's look at infinitely many local extrema. First things that should come to mind are the cosine and sine functions, right? Right? There's going to be infinitely many peaks forever, infinitely many valleys forever on both of them. So cosine and sine should come up. And infinitely many minima and maxima. Did it say 3 functions with infinitely many minima and maxima? I know there's 2. Okay, I guess the notes key says there's only 2. The notes key says that this is sine x and cosine x. I don't think there's a 3rd one, actually. So yeah, we're just going to go with what the notes key says. Miss White, I'm sure she knows best. Okay, so sine x, cosine x, okay? The 3 functions with no zeros. So this means 3 functions with no zeros. This means the graph never touches or crosses the x-axis. It never touches or crosses the horizontal axis. So let's look at those. Let's look for those, okay? Oh, sorry, I keep going to the wrong thing. Okay, no, never even touches the horizontal axis. The reciprocal function never does that, right? It has an asymptote there. Reciprocal function never does that. Exponential never does that. It also has an asymptote at y equals 0. Natural logarithm function goes right through it, so that's not true. That crosses it a million times. Exponential or logistic function right here. Logistic function, look, got an asymptote there. Never touches y equals 0, okay? So the answer here would be logistic 1 over x and e to the x, okay? All right, now they want the 3 functions. Number 24, they want the 3 functions with range all real numbers. All real numbers, what would that be? All right. So this doesn't have range all real numbers, it's bounded. This doesn't have all the real numbers. This is all the integers, right? But it never has like a y value of 1/2, so that's one real number that it doesn't have in the range. This one's bounded, so no. Bounded, no. Bounded, no. This one has a range of all real numbers, okay? It goes to negative infinity. As we go closer to 0, goes to positive infinity as x goes to positive infinity. Okay, no discontinuity, so the range is everything. No, it's bounded, bounded. This almost has a range of all real numbers, but y equals 0 is omitted. This has a range of all real numbers, right? It goes up and down forever. Bounded, so no, this has a range of all real numbers. Identity function, so it goes up and down forever, okay? So the answer here would be x cubed, x, and ln, natural log of x, okay? There we go. Number 25. The four functions that do not have end behavior, limit of f of x as x goes to infinity equals positive infinity, okay? So we're looking for the four functions that don't go to positive infinity as x goes to the right forever. So let's look at this. Let's look at this one. Oh my gosh, it's embarrassing. Okay, so this goes to positive infinity. This goes to positive infinity as x goes to the right forever. Same. This one doesn't, right? As x goes to the right forever, I'm getting closer and closer to 0. So this one, the limit is 0. This one goes up forever. Goes up forever as we go to the right. Same. This one. Okay. So the sine and cosine, they always bounce back and forth between -1 and 1, right? So they do not go to positive infinity as x goes to the right forever. They just keep oscillating between -1 and 1 forever as I go to the right. So these also do not go to positive infinity as we go to the right forever, okay? And then same for logistic. Well, logistic approaches 1 as x goes to the right forever. So the answer to this one is going to be logistic, cosine and sine, and 1 over x, the reciprocal function, okay? Number 26, we're looking for the three functions with end behavior, limit as x goes to negative infinity of f of x equals negative infinity. So as we go to the left forever, we go down forever, okay? I can think of two of those off the top of my head. Right, so up here at the top, right, identity function, as x goes to the left forever, we go down forever. X cubed function, as x goes to the left forever, we go down forever. What else? What else? The int function. Int function. As x goes to the left forever, we go down forever. Okay, in a stepwise manner. A stepwise manner. Okay. So let's go over here and write that down. So for 26, the answer is x cubed, x, and int x. Okay. The four functions whose graphs look the same when turned upside down and flipped about the y-axis. That would be the same as the odd, right? So it's the same as the odd functions. Okay, so we'll skip 27. 27, right? 27 is just saying the four functions, right? When we rotate our graphing calculator 180 degrees, they look the same. That's odd. That's the same as odd. So same as odd functions. And then the two functions whose graphs are identical except for a horizontal shift. What did we say? What did we say about that? Boom, these two, right? These are the same except, right, this vertex is shifted over to the right. Okay, so we just took the whole sine function, and then for cosine, we took this peak here and we just shifted it over to the vertical axis, right? It shifted, we took this whole thing and shifted it to the right, or to the left, depending on how you look at it. So the same except for a horizontal shift. Sine x, cosine x, okay? So those are the textbook problems that are in the notes here. So we just did all of these, okay? So slow down, rewind, pause if you need to, okay? And then the last thing in this video, thanks for bearing with me, I want to talk about number 4 here, heading 4. There's a problem on the homework which discusses this, okay? You want to sketch and list any discontinuities. So these are what's called, you should have seen them last year, these are called what's called piecewise functions, okay? So here's how we graph these. Here's how we graph these. Let me make it a little thicker. Okay. So the way this works, okay? So notice it says f of x equals x if x is less than or equal to 0. Okay, so if we're to the left of 0 or on 0, my function just looks like the identity function. Okay, if we're greater than 0, my function just looks like x squared. X squared like that, okay? So are there any discontinuities here? Well, there's no vertical asymptotes, and there's no holes. Okay, are there any jumps? There are no jumps. There are no jumps here, right? Because the first part of our graph stops at y equals 0, and the second part of our graph here, this half a parabola part, starts at 0. Okay, so there's no jumps, so no discontinuities. Okay, let's look at part B. Let's draw a decent set of coordinate axes. Oh, whoops. All right, so what are we looking at here? If x is less than 0, it looks like the reciprocal function. So I'm going to have, actually let me do pink. Looks like the reciprocal function if x is less than 0. Okay, if x is greater than, to the right of the y-axis, it looks like the square root function. Okay, is there a discontinuity here? Yes, there is, right? There is a discontinuity, okay? So as I come to x equals 0 from the right, my y just dips down to negative infinity, okay? Or if I go to x equals 0 from the left, if I go to x equals 0 from the left, my graph dips down to y equals negative infinity. But from the right, as I go to x equals 0 from the right, my y goes to 0. So there's a jump here. There's a jump discontinuity. So I think it's a jump discontinuity here. Right, so that's our discontinuity. Part C, f of x equals negative 3 minus x if x is less than or equal to 0. So these are 3 parts, 3 pieces here, okay? So we got to draw 3 different pieces. All right, so if x is less than 0, it looks like negative 3 minus x. So that's going to look like this. Y-intercept of negative 3. Slope of negative 1. Okay, that's this first piece right here. Okay, the second piece, it equals 1 if x is between 0 and 1. Okay, so at x equals 0, this graph is not equal to 1. At x equals 0 itself, I'm going to draw a hollow circle there. But between 0 and 1, drawing the hollow circle there, it is equal to 1, okay? So I put open circles here because this is a less than sign and this is also a less than sign. There's no like or equal to line there, okay? And then x squared, f of x equals x squared if x is greater than or equal to 1. Okay? So x squared, so 1 squared equals 1. So here I actually am going to end up filling this in because this third piece. And then looks like a parabola from there. X is greater than or equal to 1. Looks just like f of x equals x squared, okay? Then we can see there's a jump from here to here. There's a jump discontinuity. There's a jump. The graph jumps. So jump discontinuity at x equals 0. Okay? So hopefully that's not too convoluted. All right. Any questions, email me. But watch this video, do the 1.3 homework, and we'll see you Monday. Test next week, okay? You take care.